What if the universe is held together by an invisible cosmic web we can't fully understand? A structure so immense and mysterious that it shapes the very fabric of reality itself. This isn't science fiction. It's the profound puzzle astronomers and physicists around the world are racing to unravel. At the heart of this enigma lies dark energy, a force so strange and powerful that it makes up nearly 70% of the cosmos, yet we hardly know anything about it. Imagine something so fundamental to existence, something pushing our universe to expand faster and faster every second, and yet it remains almost entirely hidden from our view. That's the captivating mystery we're diving into today. This journey isn't just about far-off galaxies or abstract equations. It's about us, about human curiosity and our relentless drive to understand where we came from and where we're headed. For centuries, we've looked up at the night sky and wondered. Now, with tools sharper and more powerful than ever, we're on the verge of revelations that could redefine reality itself. The cosmic dark energy web isn't just an idea. It's the hidden architecture of the universe, and it influences everything from the largest galaxy clusters to the fate of time and space. And what we're starting to learn is both breathtaking and humbling. In this video, we'll explore 25 of the most mind-bending mysteries surrounding this cosmic dark energy web, questions that challenge our understanding of physics, reality, and our place in the cosmos. How does dark energy actually work? Why is the universe accelerating? What strange forces are threading this unseen web? And what happens if we one day learn to see it clearly? You're about to embark on an adventure that spans from the birth of the universe to its farthest, most uncertain future. So settle in, open your mind, and get ready to explore one of the greatest puzzles science has ever faced. For decades, the scientific community held a firm and seemingly unshakable belief about the fate of our universe. The consensus was that while the cosmos was indeed still expanding from the moment of the Big Bang, that expansion must be slowing down. It was a logical conclusion born from the fundamental understanding of gravity. Every single piece of matter, every star and every galaxy exerts a gravitational pull on every other. It seemed only natural that this collective force would act as a cosmic brake, gradually pulling the universe back together and slowing its outward rush. The biggest question wasn't if it was slowing, but by how much. Would the pull of gravity eventually halt the expansion entirely, leading to a big crunch, or would it simply coast forever at an ever-decreasing pace? This was the settled science until the late 1990s, when two rival teams of astronomers set out to measure this deceleration with unprecedented precision. Their tool of choice was a specific kind of stellar explosion known as a Type 1, a supernova. These events are extraordinary because they always explode with the same intrinsic known brightness. Think of them as the universe's perfect standard light bulbs. By observing how bright they appear to us from Earth and knowing how bright they actually are, astronomers can calculate their exact distance. Furthermore, by measuring the redshift of their light, how much it has been stretched as the universe expands, they can determine how fast the universe was moving at the time the star exploded. The plan for both teams was straightforward. Find these supernovae in incredibly distant galaxies, which means looking back in time billions of years, and measure the rate of expansion then versus now. They fully expected to see that the ancient universe was expanding faster, confirming the gradual slowdown. But the data told a completely different story, one so bizarre that the researchers initially assumed they had made a catastrophic error. The distant supernovae were significantly fainter than their calculations predicted. After painstakingly checking and rechecking for every possible source of interference, interstellar dust, instrumental flaws, miscalibrations, the only possible conclusion remaining was the unthinkable. The supernovae weren't closer, they were farther away than they should have been. This could only mean one thing: the expansion of the universe wasn't slowing down at all. It was speeding up, Some unknown repulsive force was actively pushing galaxies apart from one another, overcoming the immense gravitational pull of all the matter in the cosmos. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, had independently stumbled upon the same universe-shattering truth. The announcement of this discovery sent shockwaves through the world of physics. It was akin to throwing a ball into the air and instead of watching it fall back down, seeing it shoot faster and faster into the sky, defying everything we know about how gravity works. This wasn't just a minor adjustment to a model, it was a fundamental overhaul of our understanding of cosmic evolution. The find was so profound and the evidence so robust that in 2011, the leaders of these two groups, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics. Their work had uncovered the first direct evidence for the mysterious force we now call dark energy, the dominant component of the universe and the engine behind its accelerating expansion. It was the moment cosmology was turned on its head, proving that the universe held secrets far stranger than anyone had ever dared to imagine. And so, with the reality of the accelerating universe firmly established, we're immediately confronted by a mystery so profound it's often called the worst theoretical prediction in the entire history of physics. This is the cosmological constant problem, and to understand it, we have to rewind back to the early 20th century and the work of one man, Albert Einstein. When he was developing his theory of general relativity, which describes how matter and energy warp the fabric of spacetime to create the force we experience as gravity, Einstein faced a conceptual issue. His equations, in their original form, predicted a universe that was either expanding or contracting. But the scientific consensus at the time, including his own belief, was that the universe was static, eternal, and unchanging. To reconcile his brilliant math with this incorrect assumption, he introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant was a form of repulsive energy, a counterforce woven into the very fabric of empty space that would precisely balance the inward pull of gravity, holding the universe in a steady, unmoving state. More than a decade later, when Edwin Hubble's observations conclusively proved the universe was indeed expanding, Einstein realized his error. He reportedly called the introduction of the cosmological constant his greatest blunder and discarded it from his equations. The story, however, doesn't end there. The discovery of dark energy and the accelerating universe in the late 90s brought Einstein's blunder back from the grave with a vengeance. It turns out his cosmological constant is the simplest and most direct mathematical explanation for the dark energy we observe. That repulsive force he invented to hold the universe static is in fact the very thing pushing it apart. In a stunning twist of fate, his greatest mistake might be his most prescient insight, but here is where the problem becomes almost embarrassingly severe. We can observe the effects of this dark energy and measure its strength. It is incredibly weak, a tiny, gentle nudge causing the acceleration. Meanwhile, over in the world of quantum physics, our other great pillar of modern science, theorists have a way of calculating what the energy of empty space, the quantum vacuum, should be. Empty space isn't really empty. According to quantum theory, it's a seething, bubbling foam where virtual particles constantly flicker into and out of existence. All this frantic activity should endow every tiny cubic centimeter of nothingness with a colossal amount of energy, a vacuum energy that would act exactly like Einstein's cosmological constant. So, we have a theoretical prediction from one branch of physics and an observational measurement from another. They should match, they do not. The discrepancy between them isn't just a small error. It's a number so mind-numbingly large it defies any human scale of comparison. The amount of vacuum energy predicted by quantum theory is larger than the observed strength of dark energy by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. To try and grasp the magnitude of this error, imagine estimating the volume of the entire observable universe. Now compare that to the volume of a single proton. The difference in scale between a proton and the universe is only about 40 orders of magnitude. The error in our vacuum energy prediction is 80 orders of magnitude larger than that. It is, without exaggeration, the largest discrepancy between theory and observation in all of science. If our quantum calculations were even remotely correct, the repulsive force of this vacuum energy would have been so unimaginably powerful that it would have ripped every atom, every nucleus, every fundamental particle in the universe apart in the first instant of the Big Bang. Galaxies, stars, planets, and life would never have had a chance to form. The fact that we exist to even ponder this problem means our understanding of the quantum vacuum or the nature of dark energy is catastrophically, fundamentally wrong. This isn't just a mystery, it's a screaming clue that a deeper theory, one that perfectly unites gravity and quantum mechanics, is waiting to be found. This staggering failure of our theories to predict the most basic property of empty space brings us to our next great puzzle, one that shifts our gaze from the impossibly small to the grand sweep of cosmic history. It's a mystery not of magnitude but of timing. We call it the coincidence problem, and it asks a deeply unsettling question about our place in the cosmos. Why now? For the vast majority of the universe's 14 billion-year history, the cosmic battle was dominated by matter. The gravitational pull of both normal matter and, more importantly, the invisible clumps of dark matter dictated the evolution of everything. They gathered the primordial gas into galaxies, spun those galaxies into majestic spirals, and forged the colossal clusters that form the largest structures in existence. This was a slow, grinding process taking billions of years. Dark energy, if it was present at all, was a phantom, a whisper in the background, its repulsive force completely negligible against the overwhelming gravitational might of matter. Then something extraordinary happened. Roughly 5 billion years ago, the balance of power in the universe shifted. As the universe continued to expand, the density of matter, both dark and normal, steadily decreased. Matter dilutes as space grows. Take a box full of particles and double the size of the box, and the density of those particles falls by a factor of 8. But if dark energy behaves like a cosmological constant, its energy density remains stubbornly fixed. It is a property of space itself, so as more space comes into existence, the total amount of this repulsive energy actually increases. 5 billion years ago, the expanding universe reached a critical point. The density of matter, which had been falling, finally dropped below the constant density of dark energy. In that moment, dark energy became the dominant force in the cosmos, and the universe's expansion switched from slowing down to speeding up. This is the coincidence that keeps cosmologists awake at night. Why did this grand transition happen precisely at this point in time? Why not much earlier, when the universe was young and dense? If it had, the fierce repulsive force would have blown apart any potential for galaxies or stars to ever form, creating a forever empty, lifeless void. Conversely, why not much later? If dark energy's dominance had been delayed for many billions more years, it would have given gravity even more time to work, potentially pulling the universe into a devastating big crunch long before intelligent life could ponder its own existence. Instead, we find ourselves in a seemingly special era, a brief window where the energy densities of matter and dark energy are within an order of magnitude of each other. It's a fleeting moment in the cosmic calendar where the two titanic forces are almost perfectly balanced, and it just so happens to be the exact same moment that galaxies matured, solar systems formed, and life emerged on at least one tiny planet. The sheer unlikeliness of this timing screams for an explanation beyond mere chance. Calling it a coincidence feels profoundly unsatisfying. It points toward one of two radical possibilities. The first is the anthropic principle, the idea that the universe's fundamental constants are not necessarily fixed but could vary across a vast multiverse. In this view, we naturally find ourselves in one of the rare universes where the values of these constants, by pure chance, allowed for our existence. We shouldn't be surprised to observe this apparent fine-tuning. We literally couldn't be anywhere else. The second, and for many scientists more appealing, possibility is that dark energy is not a true constant after all. Perhaps it is a dynamic field that evolves over time, a concept that leads us directly to our next great mystery, with the coincidence problem highlighting a potentially special moment in cosmic history. Scientists are driven to investigate the true nature of dark energy itself. Is it the static, unchanging force Einstein imagined, or is it something far more dynamic and strange? To answer this, we need a way to measure its fundamental properties, and that brings us to a deceptively simple-looking letter, W. This is the equation of state parameter, and it holds the key to classifying what dark energy actually is. In the simplest terms, W describes the relationship between the pressure and the energy density of a substance. For common things we understand, this value is straightforward. For normal non-relativistic matter, like the dust and gas between stars, W equals 0. It has density but effectively no pressure. For radiation like light or the afterglow of the Big Bang, W equals 1/3 as it exerts a specific amount of pressure. For the cosmological constant model of dark energy, the value is fixed at exactly -1. This number is bizarre from a physics perspective because it signifies a negative pressure. Think about that for a moment. We are all familiar with positive pressure. It's what you feel when you push against a wall or inflate a balloon. It pushes back. A negative pressure is the opposite. It's a tension, like trying to stretch a rubber band or pull a plunger out of a syringe. It sucks instead of blows. If dark energy's W is precisely -1, it means that as the universe expands and its energy density remains constant, this negative pressure is what does the work to drive the acceleration. It is the definitive signature of a true cosmological constant, a permanent and immutable feature of the vacuum of space itself. The monumental effort in modern cosmology is to measure W with unimaginable precision to see if it truly is locked at -1. Even the tiniest deviation from this magic number would be a scientific earthquake, instantly ruling out Einstein's simple concept and opening the door to a universe of wilder possibilities. If W is even slightly different from -1, it means dark energy is not a constant. Instead, it could be a dynamic field that changes over time, much like the hypothetical field that is thought to have powered the universe's initial inflationary burst. Scientists call these theoretical fields quintessence. Unlike a static cosmological constant, a quintessence field could evolve, its strength waxing and waning across cosmic history. This would offer a natural solution to the coincidence problem, as the timing of dark energy's dominance wouldn't be a random chance but a consequence of this field's gradual evolution. The methods for measuring W are as ambitious as the question itself. Astronomers don't just look at one thing, they build a cosmic concordance, combining evidence from multiple independent sources to triangulate the truth. They use distant supernova as standard candles to map the expansion history. They study the large-scale structure of the universe, observing how the distribution of galaxies and galaxy clusters has been shaped and stretched by the competing forces of gravity and dark energy's repulsion over billions of years. They analyze the subtle patterns in the cosmic microwave background, the ancient light from the infant universe, which holds frozen imprints of how much dark energy was present at that very early epoch. Each of these probes gives a slightly different piece of the puzzle, and by combining them, researchers can constrain the value of W to an ever-narrowing range. So far, the data from missions like the Planck satellite and large galaxy surveys consistently point to a value incredibly close to -1. but the uncertainty, while small, still leaves room for thrilling possibilities. The next generation of observatories like the Vera C. Rubin Observatory and the Euclid Space Telescope are designed to shrink this uncertainty to a fraction of a percent. They will map billions of galaxies across immense volumes of space and time, providing a movie of the universe's expansion with unprecedented detail. They are hunting for a whisper of a deviation, a hint that W is perhaps negative 0.995 or negative 1.001. Such a discovery, no matter how small the difference, would be colossal. It would mean that dark energy is dynamic, that it has a history, and that the fate of our universe could be far more dramatic than a lonely, endless expansion into cold darkness. It could be accelerating towards something entirely new. To truly grasp how we can measure something as elusive as dark energy, we must journey back to the very beginning, to the oldest light we can see. This is the cosmic microwave background, or CMB, the faded afterglow of the Big Bang. For cosmologists, it's not just a static glow, it's a cosmic baby picture, a snapshot of the universe when it was a mere 380,000 years old. Before this moment, the universe was a searing, opaque plasma, so dense and hot that light couldn't travel freely. Electrons and protons were locked in a constant scatter, trapping photons in a relentless fog. But as the universe expanded and cooled, a monumental transition occurred. Electrons and protons finally combined to form neutral hydrogen atoms. In that instant, the fog cleared. The photons, suddenly freed, began streaming across the universe, and we detect that first burst of light today, cooled and stretched by 14 billion years of expansion into the microwave part of the spectrum. This ancient light is far from uniform. If you look closely with incredibly sensitive instruments, you see a tapestry of tiny temperature fluctuations, tiny spots that are ever so slightly warmer or colder than the average. These minute ripples are not random noise, they are the seeds of all future structure. They represent regions of slightly different density in the primordial plasma. The slightly denser spots, weighed down by their own gravity, would eventually collapse to form the first galaxies and the vast cosmic web. The precise pattern of these hot and cold spots across the sky is a treasure trove of information, encoding the fundamental ingredients of the cosmos: the amount of ordinary matter, the amount of dark matter, the geometry of the universe, and crucially, the amount and nature of dark energy. The connection between this infant universe and dark energy, which only became dominant billions of years later, might seem indirect, but it is incredibly powerful. Think of the CMB as the starting conditions for the entire cosmic race. By measuring the exact size and distribution of those initial density ripples, we know how the universe should have evolved under the known forces of gravity and expansion. We can run the cosmic film forward with our theoretical models. The presence of dark energy dramatically alters the outcome of that film. Its repulsive force affects how the large-scale structure of the universe, the galaxy clusters, and the vast cosmic voids forms over time. It literally changes how the universe expands from that initial state to the one we see today. This is where missions like the European Space Agency's Planck satellite come in. Planck was a masterpiece of precision, mapping the CMB's temperature and its polarization, the preferred direction of its light waves, with finer detail than ever before. By analyzing the statistical patterns of the hot and cold spots, scientists can take a sort of cosmic census. They can measure the total matter density, both normal and dark, and they can determine the geometry of the universe. The data overwhelmingly confirms that the universe is geometrically flat, meaning the rules of Euclidean geometry we learn in school hold on the largest scales. A flat universe has profound implications. It tells us that the total density of all energy and matter in the cosmos is exactly the critical density needed to balance its expansion. We already know that normal matter and dark matter together only account for about 30% of that critical density. The remaining 70% must be something else with a strong negative pressure to explain the flat geometry and the accelerated expansion. That something is dark energy. The CMB doesn't directly see dark energy, but it constrains it with an iron grip. It tells us precisely how much of this mysterious component must exist to make all the other pieces of the puzzle fit together perfectly. The observed patterns in the CMB are only consistent with our models if dark energy makes up about 68% of the universe's energy budget, a figure that aligns stunningly well with the measurements from supernova and galaxy surveys. This independent confirmation from the very dawn of time is what makes the evidence for dark energy so compelling and inescapable. It's not just one observation. It's a converging line of evidence from completely different epochs, all pointing to the same astonishing conclusion. The universe's first light, a relic from its hottest moment, quietly holds the signature of the very force that will dictate its cold, dark, and accelerating future. But to truly map the expansion history of the universe and track the growing influence of dark energy, we need more than a single baby picture. We need a series of snapshots spanning billions of years. We need a standard ruler etched into the fabric of the cosmos itself, one that remains unwavering no matter how far back in time we look. Incredibly, the universe provides exactly that, frozen into its very structure from a time when it was a seething, hot plasma. This is the mystery of Barrian acoustic oscillations, a term that sounds complex but describes a beautifully simple and powerful concept, the fossilized imprint of sound waves from the birth of the universe. To understand this cosmic echo, we need to return once more to that primordial fog, the universe before the release of the cosmic microwave background. At this time, the cosmos was a tight coupling of light and matter. Photons of light and protons and electrons, collectively known as baryons, were locked together in a constant tug of war. Gravity was the instigator. It would try to pull the plasma into denser clumps, the seeds of future structure. But the intense radiation pressure from the packed photons would fiercely push back, creating a powerful outward force that resisted the collapse. This push and pull between gravity and radiation pressure set the entire universe ringing like a bell, creating massive spherical sound waves, acoustic waves, that rippled outward through the hot plasma. These weren't gentle ripples, they were the largest waves in existence, traveling at nearly 2/3 the speed of sound through that dense medium. But this cosmic concert had a final, abrupt note. When the universe cooled enough for atoms to form at the epoch of recombination, the music suddenly stopped. The photons decoupled from the matter and streamed away, becoming the CMB we see today. Instantly, the radiation pressure vanished. The sound waves froze in place, leaving behind a lasting imprint. Each wave had traveled a specific distance from its origin point before stalling, a distance known as the sound horizon. This created a subtle but pervasive pattern, a statistical preference for galaxies to be separated by this specific, standard distance. Imagine dropping a pebble into a pond and then instantly freezing the water. The ripples would be preserved, all spaced at a fixed interval from the central point. The early universe did exactly this, but in 3 dimensions on a scale of nearly 500 million light-years. This frozen ripple, this standard ruler, is the Barrian acoustic oscillation. Its true size is imprinted with incredible fidelity in the CMB, giving us its exact measurement from the dawn of time. Now, here is the brilliant part for cosmologists. We can go looking for this same ruler at much later times in the universe's history. By conducting massive galaxy surveys that meticulously map the 3-dimensional positions of millions of galaxies across vast cosmic volumes, astronomers can look for that same preferred separation scale. They aren't looking for perfect rings in the sky. They are using powerful statistics to detect an overabundance of galaxy pairs separated by this specific distance, a faint echo of that ancient sound wave. When they measure this scale at different cosmic epochs, say, In galaxies 5 billion light-years away versus those 2 billion light-years away, they are effectively measuring how much the universe has expanded between then and now. It's like having a ruler where the markings are fixed, but the ruler itself is being stretched by the expansion of space. By seeing how much the ruler appears to have stretched, we can measure the expansion history with phenomenal precision. This is where dark energy enters the picture with undeniable force. The data from these galaxy surveys, from projects like the Sloan Digital Sky Survey and the Dark Energy Survey, reveals that the expansion history does not follow the track predicted by a matter-dominated universe. The measured scale of the Barrian acoustic oscillations at different distances shows us that the expansion began to accelerate around 5 billion years ago. The ruler's stretching tells the same story as the supernova and the CMB, but through a completely independent and incredibly robust method. These immense maps of the cosmos do more than just confirm the existence of dark energy, they allow us to probe its character. By measuring the acoustic scale in both the direction across the sky and in the redshift direction, which effectively measures time, scientists can break down the expansion history into exquisite detail. This helps them constrain that critical equation of state parameter W, telling us whether dark energy is truly constant or something that evolves. The next generation of surveys, like the Dark Energy Spectroscopic Instrument, are taking this to a whole new level, aiming to map over 30 million galaxies and quasars. They are creating a 3D movie of the universe's expansion with a clarity we've never had before, using the universe's own fossilized sound waves as the ultimate measuring tape to unravel the deepest secrets of the force that dominates our cosmic destiny. Yet for all their power as cosmic mile markers, Type 1, a supernova, are not without their own set of intricate challenges and subtleties. The core assumption is that they all explode with the same intrinsic brightness, but in reality, there is a slight natural variation. A key breakthrough was the discovery of a relationship between a supernova's peak brightness and the rate at which it fades. The slower the fade, the brighter the explosion was at its peak. This Phillips relationship allows astronomers to precisely calibrate each event, turning a good standard candle into an exceptional standardizable candle. It's akin to recognizing that while all 100-watt light bulbs are fundamentally similar, some might have slightly different colored glass. By measuring that color, you can correct for the difference and know its true output with incredible accuracy. This meticulous calibration process is what transformed these stellar explosions from interesting curiosities into the precision instruments that could detect the universe's accelerating heartbeat. The monumental discovery of the late 90s was based on just a few dozen of these distant supernovae. Today, the game has changed completely. Modern astronomical surveys are industrializing the search, scanning vast swaths of the sky night after night with automated telescopes and sophisticated software. Projects like the Zwicky Transient Facility and the upcoming Vera-C, Rubin Observatory's legacy survey of space and time, are discovering supernova by the thousands. They are not just finding more of them, they are catching them earlier in their explosion cycle, measuring their light curves with unprecedented detail, and observing them across multiple wavelengths of light from optical to infrared. This deluge of data is allowing scientists to understand the physics of the explosions themselves with far greater depth, to identify and correct for any subtle systematic biases, and to push these measurements to even greater distances, mapping the expansion history of the universe with a precision that was unimaginable just a decade ago. The ultimate goal is to use this immense new dataset to put the cosmological constant model to the most rigorous test possible. By measuring the expansion rate at many different epochs, astronomers can construct a detailed history of how dark energy has behaved over time. Has its strength remained perfectly constant, as a true cosmological constant would imply? Or is there a faint whisper of evolution, a suggestion that its repulsive power might have been slightly different in the ancient past? The answer lies buried in the light of these dying stars, and with each new supernova discovered, we get one more day to point in the grand cosmic equation, bringing us closer than ever to understanding the true nature of the force that holds the fate of the universe in its grasp. Just when we thought we had a coherent picture of our accelerating universe, a new and deeply puzzling mystery has emerged from the data, one that threatens to unravel the very foundations of modern cosmology. This is the Hubble constant tension, and it's arguably the most hotly debated topic in astronomy today. At its heart, it's a story about a single number, the Hubble constant, denoted as h0. This number represents the current expansion rate of the universe, how fast, in units of kilometers per second per megaparsec, galaxies are receding from us. A higher value means a faster expanding, younger universe. A lower value points to a slower, older cosmos. For decades, the quest for a precise value of h0 has been a central goal. The shocking development is that we now have two supremely confident, incredibly precise, yet completely incompatible ways of measuring it, and they refuse to agree. The first method is known as the distance ladder, and it's a direct continuation of Hubble's original work. This technique builds a cosmic ladder step by step, starting in our own galactic neighborhood. Astronomers use incredibly reliable objects like Cepheid variable stars whose pulsing brightness directly reveals their intrinsic luminosity to measure distances to nearby galaxies. They then use these calibrated galaxies to find Type 1, a supernova, those brilliant standard candles. By measuring how fast these galaxies and supernova are moving away from us, their redshift, and knowing their precise distance from the ladder, they can calculate the Hubble constant directly. This is a purely observational, late universe method. Teams like the one led by Nobel laureate Adam Rees have refined this technique to an astonishing degree of precision using the Hubble Space Telescope, and later the James Webb Space Telescope to eliminate systematic errors. Their consistently delivered answer points to an expansion rate of around 73 kilometers per second per megaparsec. The second method takes a completely different approach, using the cosmic microwave background as its foundation. While the CMB is a snapshot of the infant universe, it contains within its subtle temperature fluctuations a precise prediction for what the Hubble constant should be today, assuming our standard model of cosmology. The lambda CDM model, which includes dark energy and cold dark matter, is correct. Planck and other CMB missions measure the properties of these primordial ripples with exquisite detail, and when they feed this data into the model, it spits out a predicted value for the present-day expansion rate. This answer is not a direct measurement but a model-dependent inference, and it consistently gives a lower, slower value, around 67.5 kilometers per second per megaparsec. The difference seems small, only about 5.5 kilometers per second per megaparsec, but in the world of precision cosmology, it's a massive, yawning chasm. As both measurements have become more and more precise, their error bars have shrunk to the point where they now disagree with a statistical significance of over 5 sigma. In scientific terms, this means the probability that this discrepancy is just a fluke is less than 1 in a million. The tension is real. It's as if you used two different state-of-the-art stopwatches to time the same race, and one insists the winner ran a 4-minute mile while the other is absolutely certain it was a 5-minute mile. Both instruments are exquisitely calibrated, yet they tell two irreconcilable stories. This leaves cosmologists facing a thrilling and nerve-wracking possibility. Either there is a hidden, unidentified systematic error skewing one of the measurements, or our standard model of the universe is incomplete. The first option, an unaccounted-for error, is diligently being hunted. Could Cepheid variables behave differently in different galactic environments? Are there unknown complexities in the physics of supernova? The recent deployment of the James Webb Space Telescope was in part aimed at answering these very questions by observing the same Cepheids with sharper infrared eyes to cross-check the Hubble data. So far, JWST measurements have only confirmed the higher rate, deepening the mystery and making a simple observational error seem less likely. This growing confidence is what makes the second possibility so electrifying that the tension is a sign of new physics. Our standard cosmological model, for all its success, might be missing a crucial ingredient. Perhaps dark energy is not a constant but is evolving, growing stronger over time in a way that our simple models haven't captured. Maybe dark matter has properties we haven't yet discovered, interacting with itself or with light in subtle ways that alter the expansion history. There are even more exotic proposals, like the existence of a new type of dark radiation or a slight curvature to the universe that we've overlooked. Each of these ideas would tweak the universe's evolution just enough to potentially bring the early universe prediction and the late universe measurement into harmony. The Hubble constant tension is more than just a technical disagreement over a number. It's a potential doorway. It's a clear, data-driven signal that our understanding of the cosmos, from its first moments to its present acceleration, might be on the verge of a revolutionary shift. Resolving this tension isn't about proving one team right and another wrong. It's about discovering which piece of our cosmic puzzle is missing, a piece that could fundamentally change our conception of dark energy and the ultimate fate of everything we see. But the story of large-scale structure isn't just about gravity's relentless pull. It's also about a countervailing push that has dramatically reshaped the cosmic landscape over the last 5 billion years. This is where dark energy enters the narrative, not as a passive background force, but as an active sculptor in its own right. To understand its influence, we need to envision the universe not as a collection of isolated galaxies, but as a vast, interconnected network often called the cosmic web. This web is composed of dense knots where galaxy clusters reside, connected by long, thread-like filaments of gas and galaxies, all woven around unimaginably vast, empty regions known as cosmic voids. This intricate architecture is the result of a 14-billion-year tug of war between two titanic forces, the attractive pull of gravity and the repulsive push of dark energy. For the first 9 billion years of cosmic history, gravity held unquestioned dominion. It worked on the subtle density variations imprinted in the early universe, pulling matter, both the dark matter that forms the invisible scaffolding and the normal matter that lights up as stars and galaxies from less dense regions into more dense ones. This process is known as gravitational collapse. Imagine a stretchy canvas representing space with small weights placed on it. The weights create dips, and other smaller weights naturally roll down into those dips, making them deeper and more pronounced. This is how galaxy clusters formed, growing ever more massive as they pulled in matter from their surroundings. Simultaneously, the regions between these clusters were being emptied out, creating the vast, empty voids. The filaments are the highways along which matter flowed into the clusters, the last vestiges of material still in transit. For billions of years, this was the sole narrative gravity-building structure, making the rich richer and the poor poorer, creating an ever more pronounced cosmic web. The rise of dark energy fundamentally changed this story. Remember, dark energy is characterized by a negative pressure that causes the expansion of space to accelerate. This acceleration doesn't just push galaxies apart from one another. It profoundly affects the very process of structure formation. Think of it this way: for a galaxy cluster to grow, it needs to pull matter in from the surrounding filaments and void. This requires a gravitational tug strong enough to overcome the general expansion of the universe, which is constantly trying to carry that matter away. Before dark energy dominated, the expansion was slow enough that gravity could easily win this battle. But as the acceleration kicked into high gear, it became like trying to swim against a rapidly strengthening current. The expansion of space itself began to act as a drag on gravity's work, making it increasingly difficult for matter to continue flowing into the densest regions. This has a fascinating and counterintuitive effect on the cosmic web. On the very largest scales, the effect of dark energy is to suppress the formation of new structure. The grand, massive galaxy clusters we see today are essentially relics of a bygone era. They achieved most of their growth during the age of matter domination. If dark energy's influence continues to grow, it's unlikely that any future structures significantly larger than the ones we see now will ever form. The universe's construction phase for colossal projects is largely over. Furthermore, the accelerated expansion begins to stretch and distort the web itself. The vast voids, already empty, are being pushed to expand even faster than the universe as a whole, as there is very little matter inside them to provide any gravitational resistance. They are becoming ever larger and more empty. The filaments, the delicate threads connecting the nodes of the web, are being stretched and thinned, potentially even severed over immense timescales. Dark energy isn't just accelerating the expansion, it is actively isolating the structures within the cosmos, pulling the universe apart on the grandest of scales. We can't witness this billion-year drama play out in real time, so how do we possibly understand and test these ideas? The answer lies in one of the most powerful tools in modern cosmology, the supercomputer simulation. Cosmologists build virtual universes inside some of the world's most powerful computers, starting with the initial conditions from the cosmic microwave background, and then programming in the known laws of physics, gravity, fluid dynamics, and the properties of dark matter and dark energy. They can run these simulations with and without dark energy, or with different types of dark energy, and then fast forward through 14 billion years of evolution in a matter of weeks. The goal is to see which simulated universe ends up looking most like the one we actually observe through our telescopes. The results of these simulations are both breathtaking and revealing. When you include a cosmological constant form of dark energy, the virtual universe that emerges is a stunning match for reality. It produces a cosmic web with the same statistical distribution of clusters, filaments, and voids. It correctly predicts the sizes of the largest voids and the thickness of the filaments. It even reproduces the observed fact that the growth of structure has slowed down over the last few billion years. Without dark energy, the simulations produce a universe that looks wrong. It is far more clumped together, with structure growth continuing unabated and a large-scale distribution that doesn't match our painstakingly created maps of the real cosmos. This virtual evidence is a crucial, independent line of reasoning that points directly to the existence and profound influence of dark energy. It shows us that the beautiful, intricate cosmic web we see today is not just a monument to gravity's power, but also a testament to the enigmatic force that is now determining its ultimate fate. This incredible interplay between dark energy and the cosmic web brings us face to face with the grandest question of all: what is the ultimate fate of the entire cosmos? For centuries, humanity has looked to the stars and wondered how the story ends. Today, thanks to our understanding of dark energy, we can move beyond pure speculation and outline several distinct, scientifically grounded scenarios for the final destiny of the universe. The path we are on is not set in stone. It hinges entirely on the true, yet to be determined nature of dark energy itself, turning our cosmic future into one of its deepest mysteries. The first and perhaps most tranquil ending is known as heat death, or the Big Freeze. This is the future predicted if dark energy is indeed a true cosmological constant, with its equation of state locked firmly at W equals -1. In this scenario, the accelerated expansion continues forever at its current, steady pace. Over trillions upon trillions of years, the consequences unfold with a slow, inexorable majesty. Galaxies beyond our local gravitationally bound group will redshift into invisibility, their light stretched to wavelengths so long they can no longer be detected. Star formation will gradually cease as all the interstellar gas is either locked up in dead stars or ejected into the voids. One by one, stars will burn out, leaving behind cold remnants. black holes, neutron stars, and white dwarfs that slowly cool to the temperature of the background universe. Even the protons and neutrons that make up all normal matter may eventually decay if certain theories of particle physics are correct, dissolving the very bedrock of atoms into a faint mist of subatomic particles. The universe would approach a state of maximum entropy, a uniform, frigid darkness where the temperature everywhere approaches absolute zero. In this eternal equilibrium, no energy gradients remain to perform any work, no stars shine, and no complex processes can ever occur again. It is a quiet, eternal, and profoundly lonely conclusion. A second, more dramatic possibility emerges if dark energy is not a constant but something far more potent. This is the scenario of the Big Rip. If the equation of state parameter W is less than -1, meaning the dark energy field has a phantom quality, its repulsive force would not remain constant but would actually grow stronger over time. In this case, the acceleration isn't just steady, it's exponentially increasing. The fate of the universe would be not a slow fading, but a violent and catastrophic disintegration. First, the accelerating expansion would shred the cosmic web entirely, tearing galaxy clusters apart from each other. Then, the force would overcome the gravity binding individual galaxies themselves, pulling stars away from one another. As the phantom energy density continues to grow, it would eventually exceed the forces holding solar systems together, and later, the forces holding individual stars and planets together. In the final moments, just a finite time before the rip, the acceleration would become so overwhelmingly powerful that it would overwhelm the electromagnetic and nuclear forces that bind atoms and atomic nuclei. In a final, unimaginable flash, every molecule, every atom, every fundamental particle in the universe would be torn asunder from every other, ripped apart by the uncontrollable expansion of space itself. The universe would end as a diffuse, lonely sea of disconnected particles, unable to ever interact again. A third, classic ending has been largely ruled out by the discovery of dark energy, but it remains a fascinating historical footnote, the Big Crunch. This was the preferred fate before 1998, where the density of matter would be high enough to eventually halt and reverse the expansion. Gravity would win, pulling all galaxies back together in a mirror image of the Big Bang, culminating in a fiery collapse into a singular state. The discovery of acceleration means the universe is not dense enough for this to happen. There is simply too much repulsive push for gravity to ever overcome it. However, if dark energy were to somehow decay or reverse its behavior, if it were a dynamic field that eventually lost its strength, the door to this dramatic ending could theoretically be cracked open again, though there is currently no evidence to support such a turn of events. So, which of these destinies awaits us? The current evidence from supernova, the cosmic microwave background, and baryon acoustic oscillations all strongly points toward a cosmological constant. The data favors a value of W extremely close to -1, making the heat-death scenario the most likely outcome based on everything we currently know. Our universe appears to be headed for a vast, cold, and dark eternity, but the Hubble tension and the tantalizing possibility of new physics leave just enough room for doubt. The next generation of telescopes and surveys are, in a very real sense, trying to read the final chapter of the universe's story by precisely measuring this one critical number. They are working to determine whether our future is one of eternal stillness, or whether something far more strange and violent lies in wait in the deep, deep future. Faced with the immense challenge of the cosmological constant problem and the strange coincidence of our timing in the cosmos, scientists have been forced to explore radical alternatives. What if dark energy isn't a constant at all? What if it's something that changes and evolves, a cosmic chameleon whose strength has varied over the vast expanse of cosmic history? This compelling idea is known as quintessence, a theory that reimagines dark energy not as a static feature of space, but as a dynamic, rolling field. The name itself is a nod to antiquity, borrowed from the ancient Greek concept of a fifth element, a refined, elusive substance beyond earth, air, fire, and water that was thought to permeate the heavens. In modern cosmology, quintessence represents a fifth fundamental force, a new type of energy field that fills the universe and whose evolution could elegantly solve some of our most perplexing puzzles. The core distinction between a cosmological constant and quintessence is one of stillness versus motion. Einstein's lambda is frozen, an immutable property of the vacuum that remains exactly the same everywhere and for all time. A quintessence field, by contrast, is alive with potential. Think of it like a ball resting on a complex, sloping landscape. For a true cosmological constant, the ball is forever stuck at the very bottom of a deep valley. It cannot move, and its energy is forever fixed. In quintessence models, the ball is still rolling down a very gentle, very long hill. Its motion is almost imperceptibly slow, but it is moving. As it rolls, the energy associated with the field changes gradually over billions of years. This simple idea of a slowly evolving field has profound consequences, offering a possible escape from the cosmological constant's most vexing issues. Most enticingly, a dynamic quintessence field provides a natural framework for solving the coincidence problem. The puzzling observation that we live in the brief epoch where the densities of matter and dark energy are comparable. If dark energy's strength is not fixed but is instead changing, the timing of its dominance is no longer a bizarre accident of cosmic history. It becomes a predictable event in the field's evolution. In many quintessence models, the field was essentially dormant during the universe's early, matter-dominated era. Its energy density was minuscule compared to the overwhelming density of matter and radiation. But as the universe expanded and matter diluted, the quintessence field continued its slow roll, and its energy density eventually began to take over. The fact that this transition happened around 5 billion years ago isn't a staggering coincidence. It's a direct outcome of the specific shape of the field's potential energy landscape and the initial conditions set after the Big Bang. It replaces a disturbing question of why now with a more tractable one of what is the shape of this field's potential. This dynamic nature would leave a clear, detectable fingerprint on the universe, a changing equation of state. Recall that for a cosmological constant, the parameter W is precisely -1. For a quintessence field, W would generally be greater than -1, perhaps -0.95, for example, and crucially, it would vary over time. In the early universe, its value might have been different than it is today. This is the smoking gun that observational cosmologists are desperately searching for. Finding any deviation from W equals -1, no matter how slight, would instantly shatter the simple cosmological constant model and throw the doors wide open to a universe teeming with dynamic dark energy. The hunt for this signal is driving the design of the most ambitious astronomical projects of our time. Future experiments like the Vera-C, Rubin Observatory, and the Euclid Space Telescope are not simply looking to confirm the acceleration. They are forensic detectives tasked with tracing the history of W. They will achieve this by making exquisitely precise measurements of the universe's expansion history and the growth of cosmic structure across 10 billion years. By comparing the strength of gravity's pull, which builds structure, against dark energy's push, which suppresses it, these observatories can detect the subtlest whispers of a changing W. If the data reveals that dark energy's repulsive strength was slightly weaker in the past, it would be powerful evidence that we are indeed living in a universe governed by a rolling quintessence field, a cosmos where the fifth element is slowly revealing its true dynamic nature. While the cold, gradual heat death of a cosmological constant may seem like the most likely future, our journey into the nature of dark energy takes a far more dramatic and terrifying turn with the concept of phantom energy. This is not a gentle push into an endless night. It is the specter of a violent, apocalyptic end to all things. The very name evokes something supernatural and menacing, and for good reason. This theoretical form of dark energy doesn't just accelerate the universe. It promises to ultimately shred the fabric of reality itself in a cataclysm known as the Big Rip. The entire scenario hinges on that critical equation of state parameter, W. For a cosmological constant, W is exactly -1. For phantom energy, it must be less than -1. This tiny mathematical difference, a fraction of a percent on a number line, represents a fundamental shift in the behavior of the cosmos. A value of W less than -1 implies that the energy density of dark energy isn't constant. It's increasing as the universe expands. This is a deeply counterintuitive and bizarre property. Normally, any form of energy or matter dilutes as the volume of space increases. Think of air in a balloon. As you inflate it, the air molecules spread out and the density drops. Phantom energy defies this logic. Its density grows. The more the universe expands, the more of this repulsive energy there is, which causes the expansion to accelerate even faster, which creates more phantom energy in a runaway feedback loop of terrifying power. This ever-strengthening force would eventually overcome every single binding force in the universe one by one in a precise and horrifying sequence. The first structures to go would be the largest and most loosely bound. In the final tens of millions of years before the end, the accelerating expansion would become so fierce that it would overcome the gravitational pull holding galaxy clusters together. These immense cities of galaxies, which have remained gravitationally tied for billions of years, would be violently ripped apart, their member galaxies flung into the ever-expanding void. Next, the grip of phantom energy would turn its attention to individual galaxies. The gravity that binds a spiral galaxy like our Milky Way, powerful enough to orbit stars for eons, would be broken. Stars would be torn from their galactic moorings, sent flying off into isolated darkness. The final act would be swift and absolute. In the last month before the Big Rip, solar systems would be shredded. Planets would be ripped from their orbits around their parent stars. In the final minutes, the force would exceed the gravitational and electromagnetic forces holding stars and planets together. A star would simply explode, not from internal pressure, but because the space between its atoms was expanding faster than the forces that bind them. In the last infinitesimal fraction of a second, the expansion would overwhelm the very nuclear forces that hold atomic nuclei together. Every proton, every neutron, every fundamental particle would be torn apart from every other. The universe would cease to be a collection of structures or even matter. It would become a thin, ever-diluting soup of disconnected particles, unable to ever interact again. It is the most total and complete end imaginable, but is such a thing even mathematically or physically possible? Within the framework of general relativity, a substance with W less than -1 is not explicitly forbidden, but it comes with deeply strange implications. Such a phantom field would violate what physicists call the null energy condition, a principle that most classical forms of matter and energy are thought to obey. This has led some theorists to propose that phantom energy could be inherently unstable or could lead to paradoxical situations, like the possibility of negative kinetic energy or wormholes. However, it hasn't been conclusively ruled out. In fact, some theories in particle physics, particularly those involving higher dimensions or specific types of scalar fields, can naturally give rise to equations of state that dip below -1. So while it sounds like science fiction, phantom energy remains a legitimate, albeit frightening, possibility within our current theoretical landscape. The crucial question then becomes, is there any observational evidence that points toward this apocalyptic future? The answer for now is a tentative and unsettling, not yet, but we can't rule it out. Our current measurements of W from supernova, the cosmic microwave background, and baryon acoustic oscillations all converge on a value very close to -1. The uncertainty in these measurements, however, creates a window of possibility. The data might be perfectly consistent with W equals -1, but it is also statistically consistent at the outer edges of the error bars with a value slightly less than -1. We simply don't have the precision yet to slam the door on phantom energy. This is precisely why next-generation missions like the Euclid Space Telescope and the Vera-C Rubin Observatory are so vital. They are not just making more measurements, they are designing experiments to shrink those error bars around W to a vanishingly small size. They will measure the expansion history and the growth of structure with such exquisite detail that they will be able to detect even the faintest hint of a time-varying W, or a value that consistently trends below -1 across different cosmic epochs. They are, in effect, conducting a cosmic autopsy to determine the universe's ultimate cause of death. The search for phantom energy is a high-stakes game. Either we confirm our placid, cold fate, or we uncover evidence that our universe is destined for a final, unimaginable violence. The data we gather in the coming decades will tell us which specter is real. What if the single biggest assumption we've made about the accelerating universe is completely wrong? We've been exploring dark energy as a mysterious, repulsive force, but what if this force doesn't exist at all? Could it be that we haven't discovered something new in the cosmos, but instead we've been misinterpreting the oldest force we know? This is the radical proposition behind our next mystery, that dark energy is an illusion, a spectacular mirage created by our own flawed understanding of gravity itself. For over a century, Einstein's theory of general relativity has been the undisputed foundation of our understanding of gravity. It describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Planets orbit stars because they follow the curves in this cosmic fabric. This theory has passed every test with flying colors, from predicting the precise orbit of Mercury to explaining the gravitational lensing of light around massive galaxies. Its success is why physicists turn to it to explain the universe's expansion. And when that expansion was found to be accelerating, the most natural solution within Einstein's framework was to add a new component, dark energy. But a small, dedicated group of physicists is asking a heretical question: what if we're putting the cart before the horse? What if general relativity, for all its brilliance, is only an approximation, a theory that works perfectly well within galaxies and solar systems, but begins to fray at the very edges of the observable universe? This idea gives rise to a class of theories known collectively as modified Newtonian dynamics, or MUND, and its relativistic extensions. The core intuition is simple yet profound. When we look at individual galaxies, we see a puzzle. The stars at the outer edges of spiral galaxies rotate far too quickly to be held by the visible matter alone. The established solution is to invoke dark matter, an invisible substance providing the extra gravitational glue. But MUND proponents suggest a different fix. Perhaps our formula for gravity itself is incorrect on these scales. They propose that when the gravitational acceleration becomes incredibly weak, as it does in the outskirts of galaxies, Newton's and Einstein's laws need a tiny adjustment. This modification can accurately predict galaxy rotation curves without needing any dark matter. For decades, this was the main battleground, MUND versus dark matter on the scale of galaxies. But with the discovery of cosmic acceleration, a bold new claim emerged. Could a modified theory of gravity also explain the expanding universe without dark energy? The answer, according to some theorists, is a resounding yes. They are developing sophisticated new versions of gravity that go beyond general relativity. One of the most studied is known as FR gravity. The FR stands for a function of the Ricci scalar, which is a mathematical term that describes the curvature of spacetime. In simple terms, while Einstein's equations are fixed, FR gravity allows for the rules of curvature to change depending on the environment. In regions of high density, like our solar system, it behaves exactly like general relativity, preserving all its successful predictions. But in the vast, empty, low-density regions between galaxies, where the fabric of spacetime is barely curved, the modified function takes over. This alteration effectively acts as a kind of repulsive gravity, producing a cosmic acceleration that is baked directly into the laws of physics, no exotic energy required. In this view, the universe isn't being pushed apart by dark energy. It's expanding the way it is because that's simply how gravity works on the grandest scales. These theories offer an elegant philosophical appeal. They eliminate two of the biggest mysteries in cosmology, dark matter and dark energy, and replace them with a single adjustment to one of physics' most fundamental laws. It's a principle known as Occam's razor. The simplest solution is often the best. Why invent two completely new, invisible substances that have never been directly detected in a lab when you could tweak the one theory you already have? Proponents argue that modified gravity provides a more parsimonious and therefore more beautiful explanation for the universe we observe. However, this beauty is fiercely contested. The modified gravity picture faces enormous challenges, and the evidence for the standard model of dark matter and dark energy is overwhelming and multifaceted. While man can brilliantly explain the rotation of individual galaxies, it struggles catastrophically with other observations. The most famous is the bullet cluster, the result of a colossal collision between two galaxy clusters. When we observe this system, we see that the visible matter, the gas that glows in X-rays, has been slowed down and stuck in the middle of the collision by friction. But the majority of the mass, as mapped by gravitational lensing, has sailed right through the crash and lies far away from the gas. This is exactly what you would expect if that mass were made of collisionless dark matter particles. It is incredibly difficult for any modified gravity theory to explain how gravity can become disconnected from the visible matter in this way. Furthermore, the cosmic microwave background, the detailed large-scale structure of the universe, and the observed ratios of different elements forged in the Big Bang all point toward a universe that contains about 5 times more dark matter than normal matter. The patterns in the CMB are a particularly deadly blow to most simple modified gravity theories. They match the predictions of the standard model with dark matter and dark energy with astonishing precision. Creating a modified theory of gravity that can simultaneously explain galaxy rotations, the CMB, the bullet cluster, and cosmic acceleration is a Herculean task. While theories like FR gravity are making progress, they often have to introduce their own new fields and complexities, arguably making them just as contrived as the model they seek to replace. The debate is far from settled. It represents a fundamental fork in the road for cosmology. Are we living in a universe where the known laws of physics are correct, but most of its content is invisible and unknown? Or are we living in a universe where the content is simple, but our deepest understanding of how spacetime curves and expands is still incomplete? This is not just academic squabbling, it's how science progresses at the frontier. Both sides are pushing each other to refine their models and make more precise, testable predictions. The next generation of telescopes will be the ultimate arbiter, measuring the growth of structure and the history of expansion with such fine detail that they will be able to discern the subtle fingerprints that distinguish a dark energy universe from one governed by a modified law of gravity. We are forced to confront the humbling possibility that our most cherished theories are not the final word, but merely the best tools we have until the next great discovery forces us to see the cosmos in a completely new light. Yet the strange and profound connection between dark energy and black holes may run far deeper than their shared gravitational influence. Recent, groundbreaking theoretical work has begun to suggest that these cosmic paradoxes might not just interact, they could be two sides of the same coin, fundamentally linked in a way that could offer a stunning solution to our deepest cosmological puzzles. This idea emerges from the bizarre and complex world of black hole thermodynamics, a field that treats these gravitational monsters not as simple vacuum cleaners, but as incredibly exotic thermodynamic objects with properties like temperature and entropy. The story begins with Stephen Hawking's most famous revelation, Hawking radiation. He shocked the physics world by proving that black holes are not truly black. Due to quantum effects occurring right at the precipice of the event horizon, pairs of virtual particles can pop into existence. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But if this happens right at the edge of a black hole, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting a faint glow of radiation. This process causes the black hole to slowly lose mass, evaporating over unimaginable timescales. Hawking radiation directly links the three great pillars of physics: gravity, quantum mechanics, and thermodynamics. It gives black holes a temperature and defines their entropy, a measure of their internal disorder, which is proportional to the area of their event horizon. Now, enter the cosmological constant problem, that staggering discrepancy of 120 orders of magnitude between the predicted and observed energy of the vacuum. For decades, this has been physics' most embarrassing failure. But what if the error wasn't in the calculation itself, but in our assumption about where that vacuum energy actually resides? A provocative new theory proposes a breathtaking possibility that the vacuum energy predicted by quantum field theory isn't missing, it's all still there. It's just locked away, sequestered inside black holes. The argument is as elegant as it is radical. When a massive star collapses to form a black hole, it doesn't just compress matter, it potentially traps the incredibly high vacuum energy associated with that region of spacetime. According to this view, the formation of a black hole effectively takes a huge amount of quantum vacuum energy and imprisons it behind the event horizon, decoupling it from the rest of the universe and preventing it from contributing to the cosmological constant that drives cosmic expansion. In this model, the vacuum energy isn't cancelled out or somehow reduced. It is simply removed from the cosmic ledger, hidden from view where it can't exert its repulsive force on the fabric of space. The value of the cosmological constant we measure isn't the true vacuum energy. It's only the tiny, leftover amount that hasn't been locked away by all the black holes throughout cosmic history. This leads to an even more astonishing and testable prediction. If black holes are the universe's storage units for vacuum energy, then they must contain that energy in a specific form. Some theoretical work suggests this internal energy could be the source of what we perceive as dark energy. As black holes grow, primarily by accreting matter and merging with each other, they are effectively gathering and imprisoning more vacuum energy. This growth could be directly linked to the accelerating expansion of the universe. A recent study examining the growth rates of supermassive black holes at the hearts of galaxies across cosmic time found a surprising correlation. These black holes appear to have gained mass in a way that aligns with the amount of dark energy necessary to explain cosmic acceleration. It's as if the universe's expansion is being fed by the energy hidden within these dark giants. This is, of course, a highly speculative and emerging idea, and it faces significant hurdles. Many physicists question the mechanism by which vacuum energy could be so perfectly captured, and whether this model can truly account for the precise value of the cosmological constant we observe. Yet, it represents a thrilling new direction in theoretical physics. It forges a potential bridge between the incredibly small world of quantum vacuum fluctuations and the immensely large scales of cosmology, using black holes as the crucial intermediary. Instead of being isolated monsters, black holes could be active, integral players in the evolution of the cosmos, their creation and growth directly shaping the destiny of the universe itself. The hunt is now on for more evidence as astronomers meticulously measure the masses of ancient and modern black holes, searching for the subtle fingerprints of this profound connection. This brings us to one of the most profound and philosophically challenging mysteries of all, the unsettling possibility that the value of dark energy is not a random accident of physics, but a prerequisite for our own existence. This is the anthropic principle, a concept that forces us to confront the deeply strange coincidence that the universe appears exquisitely fine-tuned for life. The numbers are almost too perfect to believe. If the strength of dark energy were just slightly stronger by a factor of only a few dozen, its repulsive force would have overwhelmed gravity in the universe's infancy. In that scenario, space would have expanded so ferociously that not a single star, planet, or galaxy could have ever formed. The cosmos would be a forever empty, featureless void, devoid of any structure or complexity. Conversely, if dark energy were significantly weaker or even slightly attractive, gravity would have dominated completely. The universe might have collapsed back in on itself in a devastating big crunch long before life had any chance to emerge. We find ourselves in a breathtakingly narrow window where the values allow for a cosmos that is both structured and long-lived, a cosmic Goldilocks zone where the forces are just right. This apparent fine-tuning seems to demand an explanation beyond mere luck. The anthropic principle offers a controversial but compelling answer. The universe is suitable for life because if it weren't, we wouldn't be here to observe it. In its weakest form, this is almost a tautology, a statement of obvious selection bias. We cannot observe a universe incapable of producing observers. But in its stronger forms, the principle points toward a truly mind-bending possibility, the existence of a multiverse. The idea is that our universe, with its specific set of physical constants and laws, might be just one bubble in a vast, perhaps infinite, foam of universes. In this grand cosmic landscape, each universe could have its own unique laws of physics. Some might have no dark energy, others might have so much they tear themselves apart instantly. The vast majority would be sterile, lifeless voids, but in a few rare universes, by pure statistical chance, the numbers line up perfectly to allow for galaxies, stars, planets, and ultimately life. We find ourselves in one of those habitable universes not because it was designed for us, but because we are a product of its specific, life-allowing conditions. This idea transforms the coincidence problem from a disturbing puzzle into a potential prediction. The value of dark energy we measure isn't a fundamental law waiting to be derived from a grand theory. It is an environmental outcome, a local byproduct of our particular cosmic address within the multiverse. While this view can feel like a philosophical retreat to some scientists, a way of explaining away a problem rather than solving it for others, it is the most natural conclusion. It suggests that the quest for a single, unique theory explaining why dark energy has its specific value may be misguided. There might not be a why beyond the stark reality that this is simply one of the few values that permits our existence. The multiverse concept, while still speculative, finds support in several cutting-edge areas of theoretical physics, most notably in the theory of eternal inflation. This model suggests that the rapid expansion of spacetime that occurred during the universe's initial inflationary period never truly stopped. Instead, it continues forever in a background state, occasionally relaxing in localized pockets to form bubble universes like our own, each with potentially different physical properties. String theory, a candidate for a theory of everything, also suggests a vast landscape of possible universes, perhaps 10 to the 500 of them, each with different configurations of extra dimensions and fundamental constants. In these frameworks, the multiverse is not just a philosophical fancy, but a natural consequence of our best physical models. Yet, the anthropic principle remains deeply controversial. Its primary criticism is that it seems to stifle scientific inquiry. If we simply accept that constants are what they are because otherwise we wouldn't be here, does that mean we stop looking for a deeper, more predictive physical theory? Many physicists vehemently resist this idea, arguing that true understanding comes from equations that dictate the constants, not from statistical arguments that allow them. Furthermore, the multiverse is, by its very nature, almost impossible to test directly. If other universes are permanently disconnected from our own space-time, can we ever gather empirical evidence to confirm their existence? Some theorists propose that rare collisions between our bubble universe and another might leave an imprint on the cosmic microwave background, a circular pattern that would be the ultimate cosmic signature. So far, no such evidence has been found. The debate between the anthropic explanation and the quest for a fundamental theory represents a fundamental fork in the road for cosmology. It asks whether the deepest laws of nature are unique and inevitable, or whether they are more like a cosmic lottery ticket, one that we, against all odds, happen to win. This isn't just an academic debate, it shapes the entire direction of scientific research. Are we searching for the one equation that defines reality, or are we mapping the contours of a single habitable region within a far vaster and more bizarre cosmic ensemble? The value of dark energy sits at the heart of this question, a constant that is either a profound clue waiting to be deciphered or a quiet announcement that we are living in a very special place for now. But what if the grandest mystery of all isn't a force but a place? Imagine for a moment that our entire observable universe, all 93 billion light-years of it, isn't a representative sample of the cosmos. What if we are, by a staggering cosmic coincidence, sitting in the middle of an immense and mostly empty region, a void so vast that it distorts our entire view of reality? This is not a fringe idea, it's a serious, albeit radical, challenge to the standard model of cosmology, one that suggests dark energy itself might be the grandest illusion of all, a phantom born from our unfortunate location in an uneven universe. To understand this, we need to shift our perspective on the cosmos. The cosmological principle is a foundational idea in modern astronomy. It states that on sufficiently large scales, the universe is homogeneous and isotropic. It looks roughly the same in every direction and from every location. This assumption is what allows us to take our local observations, like the redshift of distant supernova, and extrapolate them to the entire cosmos, concluding that dark energy is a universal phenomenon. But what if that principle is wrong, or at least, what if the scales required for true homogeneity are far larger than we can possibly observe? This opens the door to a class of models known as inhomogeneous cosmologies, where the universe is more like Swiss cheese, with dense clusters and filaments of galaxies surrounding incredibly vast, empty voids. In this scenario, our Milky Way galaxy might not be in an average neighborhood. We could be residing in an underdense region, a cosmic backwater where the density of matter is significantly lower than the true cosmic average. Gravity's behavior is directly tied to the density of matter around it. Inside a giant void, the gravitational dynamics are completely different. The relative lack of surrounding matter means there's less gravitational tug holding our local region together. From our vantage point deep inside this emptiness, the distant universe outside our void would appear to be accelerating away from us at an increasing rate. Why? Because the matter-rich regions outside are feeling a stronger gravitational pull from their densely packed neighbors, slowing their expansion relative to ours. Our local space with weaker gravity would expand faster, making it seem as if everything beyond our void is being pushed away by some mysterious repulsive force. We would misinterpret this faster local expansion as a global acceleration, inventing dark energy to explain an effect that is purely geographical. The idea gains traction when we look at the actual maps of our cosmic neighborhood. Astronomers have indeed identified some colossal voids. The KBC void, named for astronomers Keenan, Barger, and Cowie, is a proposed spherical region about 2 billion light-years across, with our Milky Way sitting near its center. If confirmed, it would be the largest known structure in the universe, a staggering volume of relative emptiness. Similarly, the Boötes void is a famous and eerily empty spherical region about 330 million light-years in diameter, containing far fewer galaxies than expected. Proponents of the void model argue that we don't need to look for exotic new physics. We simply need to account for the gravitational effects of living in such an immense underdense region. The perceived acceleration could be explained by the well-understood laws of general relativity applied to an irregular mass distribution, no dark energy required. However, this seemingly elegant solution faces monumental challenges. The primary hurdle is the cosmic microwave background. The pattern of hot and cold spots in the CMB is a snapshot of the universe's density distribution at a very early time. The statistics of these fluctuations are exquisitely consistent with a universe that is homogeneous on large scales. For a local void to mimic dark energy, it would have to be unimaginably large and deep, and its existence would leave a very specific and detectable imprint on the CMB radiation that passes through it, an effect known as the Rees-Simon or integrated Sachs-Wolfe effect. We do see such an imprint, but it is actually used as evidence for dark energy, as its signature is consistent with a smooth, pervasive component causing accelerated expansion. Creating a void model that can also explain the precise details of the CMB has proven incredibly difficult, often requiring a void so vast and specially shaped that it begins to seem just as contrived as the thing it's trying to replace. The debate ultimately comes down to a choice between two extraordinary propositions. On one hand, we have dark energy, a mysterious, dominant component of the universe that we cannot directly see or explain within our current physical theories. On the other, we have the possibility that we occupy a privileged and profoundly special position in the cosmos, a possibility that directly contradicts the Copernican principle that we do not live in a special place. It is a classic scientific standoff between inventing new physics and questioning our fundamental assumptions about the universe's structure. While the evidence currently weighs heavily in favor of dark energy and a homogeneous universe, the void hypothesis remains a vital and compelling alternative. It forces cosmologists to rigorously test their assumptions and ensures that the case for dark energy is built on a foundation that can withstand such radical challenges, reminding us that in the quest to understand the cosmos, even our most basic premises must be held up to the light. But what if the deepest laws of physics, the very rules that govern reality, actually forbid the existence of the thing we're trying to explain? This isn't a plot twist from a science fiction novel. It's a serious theoretical dilemma emerging from our most ambitious attempt at a theory of everything, string theory. The controversy is known as the swampland conjecture, and it throws a massive wrench into the simple, elegant idea of a cosmological constant, suggesting that our entire understanding of dark energy might be built on theoretical quicksand. To grasp this high-stakes conflict, we first need to understand the playing field. String theory proposes that the fundamental constituents of the universe are not point-like particles but tiny, vibrating strings. The different vibrations of these strings correspond to different particles and forces. For this theory to be mathematically consistent, it requires more than the three spatial dimensions we experience. It needs extra dimensions, often 6 or 7 of them, curled up into unimaginably small, complex shapes known as Calabi-Yau manifolds. The specific way these dimensions are folded determines the physical laws and constants we observe in our 4-dimensional world, like the strength of gravity or the value of the cosmological constant. The set of all possible configurations of these extra dimensions that yield a consistent, mathematically sound universe is called the string theory landscape. This landscape is thought to be vast, potentially containing 10 to the 500 different possible universes, each with its own unique set of physical laws. Now, surrounding this landscape is what theorists call the swampland. This is a brilliant and evocative metaphor for the set of theories that look perfectly reasonable from a low-energy, four-dimensional perspective, but are ultimately incompatible with the full quantum gravitational framework of string theory. They are theories that might seem to work on their own but can never be completed into a consistent theory of quantum gravity. They are, in essence, stuck in the swampland, theoretically dead ends. Over the past decade, physicists have been trying to map the border between the landscape and the swampland, formulating a set of criteria known as the SW-plan conjectures. These are rules that any effective theory must obey to have a chance of being connected to a full theory of quantum gravity. One of the most impactful of these conjectures directly takes aim at dark energy. It's often called the de Sitter conjecture, named after the type of universe a positive cosmological constant would create, a de Sitter space. This conjecture suggests that it is impossible to achieve a stable, positive cosmological constant in a true theory of quantum gravity. In simpler terms, a universe with a true, unchanging vacuum energy that drives accelerated expansion might actually live in the swampland. It might be theoretically forbidden. The conjecture proposes a specific, testable constraint that the potential energy of any field that could act like dark energy must not be constant, and its slope must be steep enough relative to its height. In even simpler terms, dark energy cannot be a perfect cosmological constant. It must be dynamic, like a quintessence field that evolves over time. Furthermore, the allowed values for this field are constrained, potentially ruling out the very tiny value we observe. The implications of this are nothing short of seismic. If the swampland conjectures are correct, then our standard model of cosmology, lambda CDM, with its perfectly constant dark energy, is not just incomplete, it's fundamentally wrong and impossible to reconcile with string theory. The universe isn't just expanding, it's expanding in a way that the laws of quantum gravity supposedly do not allow. This creates a direct and dramatic conflict between our observations of the cosmos and our leading candidate for a theory of everything. So, how do we resolve this? One possibility is that the swampland conjectures are incorrect or need refinement. String theory is a work in progress, and these conjectures are just that, informed conjectures, not proven theorems. Perhaps there is a clever, yet to be discovered mechanism within string theory that can indeed produce a stable de Sitter vacuum, placing our universe back in the habitable landscape. The other possibility is that our interpretation of the observations is wrong. This is where the hunt for a dynamic dark energy becomes absolutely critical. The swampland conjectures predict that dark energy must be dynamic. Therefore, if next-generation telescopes like Euclid and the Rubin Observatory can find even the slightest evidence that the equation of state parameter W deviates from -1, or that it has changed over time, it would be a monumental victory not just for observational cosmology, but for string theory itself. It would provide the first empirical hint that the conjectures are on the right track and that our universe is governed by a rolling quintessence field, perfectly aligning with the demands of quantum gravity. The swampland conjecture transforms the mystery of dark energy from a purely cosmological puzzle into a profound test of fundamental physics. It pits our largest-scale observations against our smallest-scale theories, forcing a dialogue between the universe we see and the universe that might be mathematically possible. The outcome will determine more than just the fate of the cosmos. It will determine the fate of our most cherished theories about how it all works. We are in a race to see whether our maps of the universe's expansion can guide us safely through the theoretical swampland, or whether we'll need to redraw our understanding of reality itself. Perhaps the greatest quest in all of physics is the search for a single, unified theory that can seamlessly marry the two colossal pillars of modern science: the cosmic gravity of general relativity and the subatomic weirdness of quantum mechanics. For decades, this theory of quantum gravity has remained elusive, a holy grail just beyond our reach. And now, in a stunning twist, the mystery of dark energy might be the very key that finally unlocks the door. It's as if the universe handed us its most perplexing riddle and whispered that the answer might also be the solution to everything else. To understand why this connection is so profound, we need to appreciate the fundamental conflict. General relativity paints a beautiful picture of gravity as the smooth, geometric curvature of spacetime, a stage on which the cosmic drama unfolds. Quantum mechanics, on the other hand, reveals a frantic, probabilistic world where particles flicker in and out of existence and fields are forever jittering with uncertainty. These two descriptions are brilliant in their own domains, but they become utterly incompatible when forced together, especially in extreme environments like the center of a black hole or the first moment of the Big Bang. The mathematics simply breaks down, producing nonsensical infinities. This schism tells us that our understanding of reality is incomplete. We are missing the master theory, the deeper framework from which both gravity and quantum physics naturally emerge. Dark energy, and specifically the cosmological constant problem, is where this theoretical crisis becomes impossible to ignore. Remember that staggering error of 120 orders of magnitude. That's not just a small miscalculation, it's a screaming siren that our two best theories are giving us completely contradictory answers about the most basic question imaginable: what is the energy of empty space? Quantum field theory, with its description of virtual particles bubbling in a vacuum, predicts a universe-ending amount of repulsive energy. General relativity, when we plug in the observed acceleration, measures a gentle, barely there nudge. This isn't a minor accounting error, it's a fundamental disagreement about the very fabric of reality. Therefore, any theory that hopes to be a true theory of quantum gravity must, first and foremost, be able to resolve this catastrophic discrepancy. It must explain why the quantum vacuum doesn't gravitate with the insane strength our math says it should. In this way, dark energy isn't a side issue. It is the central litmus test for any candidate theory of everything. This has led physicists to explore some of the most mind-bending concepts ever conceived. One revolutionary idea is the holographic principle, which suggests that all the information contained within a volume of space, like our entire three-dimensional universe, might actually be encoded on a two-dimensional surface that surrounds it, like a cosmic fingerprint on a bubble. It's a concept that sounds like it's straight out of science fiction, but it emerges naturally from the physics of black holes and their entropy. If this principle is true, it would mean our perception of a three-dimensional reality is a kind of magnificent illusion, a projection from a deeper, lower-dimensional reality. How does this connect to dark energy? In a holographic universe, the number of fundamental degrees of freedom, the basic bits of information, is drastically reduced compared to a standard quantum field theory calculation. This reduction could naturally suppress the vacuum energy to the tiny, observed value, effectively solving the cosmological constant problem by telling us we've been overcounting the true number of contributors to the vacuum's energy. The repulsive force we call dark energy could be a subtle consequence of this cosmic hologram. Another fascinating avenue involves the very nature of spacetime itself. Both general relativity and quantum field theory treat spacetime as a smooth, continuous background, a static stage. But what if that stage is itself made of something more fundamental? Theories like loop quantum gravity propose that spacetime might be granular at the smallest possible scale, woven from discrete, finite loops or atoms of space and time. This pixelation of reality would occur at the unimaginably tiny Planck length, far beyond our current ability to probe directly. In such a framework, the frenetic dance of virtual particles that quantum theory predicts would be subject to a fundamental limit. They couldn't fluctuate on scales smaller than this elementary grain. This natural cutoff could tame the wild infinities of the quantum vacuum calculation, bringing the predicted energy down from its universe-shattering value to something much closer to what we observe. In this view, dark energy is not a mysterious substance, but a remnant effect, an echo of the discrete quantum nature of spacetime itself. The challenge, of course, is that these ideas exist primarily in the realm of profound mathematical speculation. We lack the experimental technology to directly probe the Planck scale or to test the holographic nature of the universe, but this is where dark energy offers a unique opportunity. It provides a cosmological observable, the accelerating expansion of the entire universe, that might be the only large-scale shadow cast by these incredibly small-scale phenomena. By meticulously measuring the properties of dark energy, its equation of state, and whether it changes over time, we are effectively collecting forensic evidence from the crime scene of the Big Bang, looking for clues about the quantum structure of spacetime. Each new constraint on the value of W from telescopes like Euclid isn't just filling in a parameter in a model. It's providing crucial data that could validate or rule out some of the most ambitious ideas about quantum gravity ever conceived. The fate of the cosmos and the fundamental nature of reality are intertwined in a single, breathtaking mystery. Yet for all our profound theories and daring conjectures, the ultimate answers to the dark energy puzzle won't come from pure thought alone. They will be delivered by a new generation of cosmic cartographers, telescopes of such staggering power and precision that they will transform this philosophical debate into a matter of definitive data. We are standing on the precipice of a new golden age of observational cosmology, where missions designed with one primary goal, to unravel the mystery of dark energy, are now scanning the skies or preparing for launch. These are not merely incremental upgrades, they are revolutionary instruments that will map the universe in unprecedented detail, collecting more data in a single night than previous surveys gathered in years. Leading this charge from the ground is the Vera C. Rubin Observatory, a facility that represents a paradigm shift in how we study the cosmos. Perched high in the Chilean Andes, its cornerstone is the Legacy Survey of Space and Time, a 10-year endeavor that will photograph the entire available southern sky every few nights. This isn't a static map, it's a high-definition movie of the universe. The scale is almost incomprehensible. The survey will detect and measure tens of billions of galaxies and track the brightness of over 20 billion stars within our own Milky Way. Its primary camera is the largest digital camera ever built for astronomy, a technological marvel with a resolution so high you would need hundreds of ultra-high-definition televisions to display just one of its images at full size. For dark energy, this relentless all-sky patrol is invaluable. By discovering and meticulously monitoring millions of distant Type Ia supernova, Rubin will trace the expansion history of the universe with unrivaled precision. But it will do far more than that. By measuring the subtle distortions in the shapes of billions of galaxies caused by gravitational lensing, a phenomenon where massive structures bend the fabric of space-time, and the light traveling through it, the survey, will create a colossal 3D mass map of the dark matter scaffolding of the cosmos. This will allow scientists to see directly how the competition between gravity's pull and dark energy's push has shaped the growth of structure over billions of years, providing a critical independent test that will tightly constrain the nature of W. While Rubin paints its grand panorama from the ground, the Euclid Space Telescope is already offering a crystal-clear view from above Earth's blurring atmosphere. Launched by the European Space Agency, Euclid is a dedicated dark energy hunter designed to measure the geometry of the dark universe with exquisite accuracy. Its strategy is twofold. First, it will perform a gigantic galaxy redshift survey, measuring the precise distances to over 1 billion galaxies across 10 billion light-years of cosmic history. This immense catalog will be used to find the cosmic ruler of baryon acoustic oscillations at different epochs, allowing us to see exactly how the universe's expansion has changed over time. Second, Euclid's incredibly sharp optics will conduct a weak gravitational lensing survey over a third of the sky. By observing how the images of distant galaxies are ever so slightly stretched by the invisible web of dark matter that lies between them and us, Euclid will trace the distribution of mass in the universe. Even more importantly, it will track how the clumpiness of this matter has evolved. The growth of these cosmic structures is exquisitely sensitive to the repulsive force of dark energy. If dark energy is a true cosmological constant, the growth of structure should have slowed down over the last 5 billion years. If it's something else, like quintessence, the suppression might follow a different pattern. Euclid's measurements will detect these differences, offering a powerful verdict on the simplest models. Joining this effort later this decade is NASA's and Nancy Grace Roman Space Telescope, often called Hubble's wide-eyed cousin. While Hubble and JWST peer deeply at tiny patches of sky, Roman is designed for a grand, wide-field survey of breathtaking scope. Its core dark energy investigation will be through one of the largest galaxy redshift surveys ever conducted, mapping the positions of millions of galaxies. But Roman brings a unique and powerful capability to the table. It will conduct a high-resolution survey of Type Ia supernova entirely from space. This is a game-changer. From the ground, observing these distant explosions is a constant battle against atmospheric turbulence, interstellar dust, and the limitations of only being able to observe at night. Roman, operating above all that, will capture these supernovae with phenomenal clarity and consistency, free from the systematic errors that can plague ground-based observations. It will find them farther away and measure their light curves with a precision that could finally reveal the tiny deviations in brightness that might signal a dynamic form of dark energy. Together, these three observatories, Rubin, Euclid, and Roman, form a complementary alliance. They will attack the problem from every angle: supernova, baryon acoustic oscillations, and weak lensing. They will cross-check each other's results, eliminate systematic errors, and build an ironclad case for the true history of the universe's expansion. The data these missions will produce is not just more of the same, it's of a fundamentally different kind. It's the difference between a handful of weather stations and a global network of Doppler radar. Previous surveys gave us key data points. These new observatories will provide a continuous, high-fidelity record. They won't just measure the equation of state parameter W, they will track its potential evolution over cosmic time, a measurement known as W of A. Finding that W is not constant would be the smoking gun for quintessence and a monumental revolution in physics. It would instantly invalidate the simple cosmological constant model and force us to confront a universe where dark energy is a dynamic, evolving player. Furthermore, this torrent of data will provide the most stringent tests yet for alternative theories like modified gravity. The detailed maps of the cosmic web's growth will reveal subtle signatures, how galaxies cluster, how voids expand, that are uniquely predicted by theories that alter Einstein's equations. The data will either confirm the standard model of dark energy and dark matter beyond a reasonable doubt, or it will reveal cracks so significant that a whole new physics will be required. We are not just building better telescopes, we are constructing the machines that will write the next chapter of fundamental physics, using the universe itself as their laboratory. Imagine a universe where the very force driving its expansion is not a fixed, immutable constant, but a dynamic entity with its own history, slowly changing its strength over billions of years. This isn't a far-fetched fantasy, it's a serious scientific possibility that lies at the heart of one of the most refined quests in modern cosmology. We've grown accustomed to thinking of dark energy as Einstein's cosmological constant, a static force woven into the fabric of space. But what if that's not the full story? The haunting coincidence of its recent dominance and the staggering failure of quantum physics to predict its strength both whisper that there might be more to learn. The key to unlocking this deeper mystery lies in chasing a ghost, a potential evolution in dark energy's power that would rewrite everything we think we know. This entire investigation hinges on a deceptively simple question. Does the equation of state parameter W change over time? For a true cosmological constant, the answer is a definitive no. Its value remains locked at precisely -1 from the Big Bang to the distant future. But if we were to find even the tiniest deviation from this value, or better yet, evidence that it was different in the past, it would be the equivalent of a cosmic earthquake. Such a discovery would instantly shatter the simple cosmological constant model and throw the doors wide open to a universe of dynamic possibilities, chief among them the concept of quintessence. This theoretical dynamic field would roll along its own energy landscape, its repulsive strength waxing and waning across the eons, offering a natural explanation for why it only became dominant at this specific point in cosmic history. Detecting such a subtle variation is arguably the greatest technical challenge observational cosmology has ever faced. We are not looking for a massive signal. We are hunting for a whisper of a deviation in a number that is already incredibly close to -1. To have any hope of success, scientists must become masters of cosmic forensics, reconstructing the expansion history of the universe with painstaking precision across billions of years. This requires multiple, independent lines of evidence, each serving as a cross-check against the others. The primary tool is still the Type Ia supernova, the cosmic standard candle that first revealed the acceleration. But now, instead of a few dozen, surveys are discovering thousands of these events, measuring their light curves with exquisite detail, and pushing them to ever greater distances to see how the expansion rate behaved in the universe's youth. This is complemented by the cosmic ruler of Bowerian acoustic oscillations. Remember, we know the true physical size of these frozen sound waves from the cosmic microwave background. By measuring their apparent size in galaxy maps from different epochs, we can see exactly how much the universe has stretched between then and now. If dark energy's strength has been changing, it would leave a specific fingerprint on this stretching, a subtle distortion that would tell us the expansion history wasn't quite what a simple cosmological constant would predict. Finally, there is the growth of cosmic structure itself. The battle between gravity's pull, which builds galaxies and clusters, and dark energy's push, which suppresses this growth, is exquisitely sensitive to the nature of the repulsive force. A changing dark energy would alter the timeline of how the cosmic web formed, leaving an imprint on the clumpiness of matter that powerful telescopes can detect by watching how galaxies cluster together across vast distances. This is the monumental task that a new generation of observatories has been designed to undertake. The Vera C. Rubin Observatory's legacy survey of space and time will scan the sky relentlessly, discovering millions of supernova and mapping the shapes and positions of billions of galaxies to measure both the expansion history and the growth of structure. The Euclid Space Telescope, operating from the pristine environment beyond Earth's atmosphere, is performing a giant redshift survey and a weak lensing map of unparalleled precision, specifically to measure the BAO ruler and the clumping of matter across cosmic time. NASA's Nancy Grace Roman Space Telescope will join this effort, using its sharp, wide-eyed gaze to capture supernova with unmatched consistency from space, free from the distorting effects of our atmosphere. Together, these missions are not just making more measurements, they are building a high-definition, multi-dimensional movie of the universe's evolution. They will measure the value of W and its potential time variation, denoted as WA, with a precision that is an order of magnitude better than anything we have today. The goal is to shrink the error bars on these parameters so dramatically that we will finally have a definitive answer. They are hunting for a signal so faint that it might be a deviation in the second or third decimal place, a whisper that W is negative 0.99 or negative 1.01, and that this value was different 10 billion years ago. Finding such a signal would be one of the most profound discoveries in the history of science. It would confirm that dark energy is a dynamic field, a new fundamental ingredient in the universe that evolves and interacts with the cosmos in a complex dance. It would provide a natural solution to the coincidence problem, as the timing of its dominance would no longer be a random accident but a consequence of its gradual evolution. It would also provide crucial guidance for theorists, pointing them toward the specific class of physical models that could explain this behavior, potentially offering a bridge to a deeper theory of quantum gravity. We are on the verge of determining whether the force that holds the fate of the universe is a steady, eternal constant or a dynamic player with its own story to tell. The answer will define not just our cosmic future, but our fundamental understanding of physical reality. But to truly understand the subtle, ghostly imprint dark energy leaves on the oldest light in the universe, we need to follow the journey of a single photon from the dawn of time. Picture this photon, a particle of light from the cosmic microwave background, beginning its journey 14 billion years ago. It's finally free, racing away from the hot plasma of the infant universe. For billions of years, it travels undisturbed through the vast, expanding cosmos. But its path is not through empty space. It's navigating an invisible landscape of hills and valleys, the gravitational potentials created by the cosmic web of dark matter. As this photon approaches a massive galaxy cluster, a deep gravitational well, it must climb out of this cosmic valley. In doing so, it loses energy, and we perceive that energy loss as a slight redshifting, a cooling of its light. Conversely, when it falls into a gravitational well, it gains energy, blue shifting to a slightly warmer temperature. In a universe dominated solely by matter, where the growth of these structures is linear and predictable, these gains and losses would perfectly cancel out over the photon's long journey. The temperature of the CMB would remain a near-perfect blackbody, its tiny fluctuations frozen in time since the moment of recombination. This is where dark energy changes the story entirely. By causing the expansion of the universe to accelerate, dark energy begins to suppress the formation of new large-scale structure. More importantly, it actually causes the existing gravitational potentials, those hills and valleys of the cosmic web, to slowly decay and become shallower over time. The universe's frantic expansion starts to stretch and smooth out the very fabric of these gravitational landscapes. Now, let's rejoin our photon on its multi-billion-year voyage. When it enters a gravitational well, it gains energy and blue shifts, but by the time it exits that same well, the well has become shallower due to the influence of dark energy. The photon doesn't have to work as hard to climb out, so it doesn't lose all the energy it gained on the way in. There's a net gain. Conversely, if a photon loses energy climbing out of a well that later becomes deeper, it would experience a net loss. This subtle, non-canceling effect, this slight heating or cooling of CMB photons as they traverse these evolving gravitational landscapes, is known as the integrated Sachs-Wolfe effect. It's a direct and measurable consequence of a universe whose expansion is accelerating, a universe where dark energy is at work. Detecting this effect is a monumental challenge. The temperature changes involved are incredibly minuscule, on the order of millionths of a degree. It's not something you can see by looking at a single spot on the CMB map. The key is in the statistics, in finding a correlation between the distribution of matter in the nearby universe and the temperature patterns in the ancient CMB. Astronomers take a detailed map of millions of galaxies and quasars, a snapshot of the large-scale structure from the last few billion years. and they cross-reference it with the Planck satellite's exquisitely detailed map of the cosmic microwave background. The question they ask is a simple yes or no. Are the slightly warmer spots in the CMB statistically more likely to be aligned with the positions of immense superclusters of galaxies? And are the slightly cooler spots more likely to be aligned with the vast, empty cosmic voids? In a universe without dark energy, where the gravitational potentials are static, there should be no correlation. The patterns should be completely random relative to each other. Yet, that is not what the data shows. After painstaking analysis, a significant correlation has indeed been found. The warm spots in the CMB do subtly align with the underdense voids, and the cool spots with the overdense clusters. This is the smoking gun. It means that CMB photons passing through voids are slightly warmer than average. They've experienced a net energy gain because the void's gravitational hill has become shallower during their travel. Photons passing through clusters are slightly cooler. They've lost a net amount of energy because the cluster's valley has decayed. This independent statistical whisper from the fading echo of the Big Bang provides powerful, corroborating evidence for the existence of dark energy. It's a completely different line of reasoning than supernova or baryon acoustic oscillations, one that ties the fate of the ancient radiation directly to the evolution of structure in the late-time universe, offering a unique and compelling confirmation that something is indeed causing the cosmos to stretch at an ever-increasing rate. But amid the grand cosmic maps and the subtle whispers from ancient light, one of the most intriguing clues might be hiding in the realm of the impossibly small, with a particle so elusive it barely seems to interact with our world at all. This brings us to a fascinating and deeply speculative intersection between two of physics' greatest puzzles, dark energy and the ghostly neutrino. On the surface, they seem to inhabit completely different domains, one a vast, smooth force driving the universe apart, the other a tiny, fast-moving particle that zips through matter as if it weren't even there. Yet, some theorists are beginning to suspect that their connection might be far more than just cosmic coincidence, proposing that these ethereal particles could hold a key to understanding the accelerating expansion. To see how this could possibly work, we first need to appreciate the strange nature of neutrinos themselves. Billions of them are passing through your body every second, emitted by the sun, distant supernova, and even the radioactive decay of elements within the Earth. They are often called ghost particles because they barely interact with normal matter. Their chances of hitting an atom are astronomically low. For decades, they were thought to be entirely massless, traveling at the speed of light. But groundbreaking experiments at the turn of the millennium revealed something shocking. Neutrinos oscillate. That is, they can change their identity, flipping between three different types: electron, muon, and tau neutrinos. This remarkable behavior is only possible if they have mass, a discovery that earned the researchers the Nobel Prize. Yet this mass is impossibly tiny, less than a millionth of the mass of an electron. We know they have mass, but we still don't know exactly how much, and this very uncertainty opens a door to a profound cosmic connection. The potential link to dark energy arises from considering the density of these particles throughout cosmic history. In the very early, incredibly hot and dense universe, neutrinos would have been flying around at nearly the speed of light. Relativistic particles like this exert a positive pressure, contributing to the expansion rate in a specific way. But as the universe expanded and cooled, these neutrinos would have slowed down. When a particle transitions from moving at relativistic speeds to non-relativistic speeds, its behavior changes dramatically. It begins to act more like cold matter, clumping together under gravity rather than helping to smooth the universe out. The timing of this transition for neutrinos is critically dependent on one thing: their mass. Heavier neutrinos would have slowed down and become non-relativistic earlier in the universe's history. This is where the plot thickens. What if the transition of neutrinos from a relativistic state to a non-relativistic state somehow triggered or influenced the onset of dark energy's dominance? It's a tantalizing thought because the estimated time when the most massive neutrinos became non-relativistic roughly coincides with the epoch, around 5 billion years ago, when dark energy took over the cosmic energy budget. Could this be another layer to the coincidence problem, or is it a clue to a direct physical mechanism? Some bold theories propose exactly that, suggesting that dark energy isn't a static background but a dynamic field that interacts with neutrinos through a new, fundamental force. This idea is known as the growing neutrino quintessence model, and it is as elegant as it is radical. In this scenario, dark energy is indeed a dynamic quintessence field, slowly rolling down its potential. Initially, its energy density is too weak to have any noticeable effect, but this field is coupled to neutrinos. As the universe expands and neutrinos cool, eventually becoming non-relativistic, this change in the neutrino's behavior acts as a trigger. It subtly alters the shape of the potential energy landscape that the quintessence field is rolling down, causing the field to suddenly stall and freeze. When a rolling field like this gets stuck, its energy density can become nearly constant, mimicking a cosmological constant and beginning to dominate the universe. In this model, the neutrinos act as a cosmic clock. Their inevitable cooling and slowing, dictated by the expansion of the universe, provides the signal that tells the dark energy field to switch on its repulsive force. It elegantly solves the "why now" problem by linking the acceleration of the universe to a specific, predictable event in particle physics. The implications of such a coupling are staggering. It would mean that the properties of the smallest known massive particles are directly dictating the ultimate fate of the entire cosmos. Furthermore, this interaction would not be a one-way street. If a dark energy field is coupled to neutrinos, it could be transferring energy to them, potentially causing their masses to change over time. This is a testable prediction. By looking at the distribution of galaxies on the largest scales and the precise patterns in the cosmic microwave background, cosmologists could potentially detect the faint signature of neutrinos whose mass was different in the ancient past compared to today. It would be a revolutionary discovery, showing that the laws of physics are not frozen in time but are part of a dynamic, evolving cosmic dialogue between the largest and smallest scales. While still highly speculative, this mysterious connection forces us to consider that the answers to cosmology's biggest questions might be found not only in the void of space but in the hidden nature of the most elusive particles in existence. But to truly grasp the cosmic tug-of-war orchestrated by dark energy, we need to shift our perspective from the grand architecture of the cosmic web to the specific, individual motion of each galaxy within it. This brings us to a subtle yet profound distortion in the very fabric of expansion known as the Hubble flow. Imagine the universe's expansion not as a perfectly smooth, uniform stretching, but as a mighty river flowing outward from the Big Bang. This is the Hubble flow, the overall current of expansion where, on average, a galaxy's recessional velocity is perfectly proportional to its distance from us, a relationship encoded in the Hubble constant. For decades, we've pictured galaxies as leaves floating on this river, carried along by the relentless current of expanding space. But this serene picture is an oversimplification. Each galaxy is not just a passive passenger, it also has its own peculiar motion, a local drift caused by the gravitational tug of its immediate neighbors, like a leaf caught in a small eddy or ripple while still moving with the river's main current. These peculiar velocities are the key to mapping the invisible mass of the universe. The gravitational pull of a massive galaxy cluster will cause nearby galaxies to fall toward it, adding a component of motion that either slightly speeds up or slows down their recession relative to the pure Hubble flow. For a century, astronomers have used these motions to weigh clusters and map the distribution of dark matter. But dark energy adds a stunning new layer of complexity to this dance. As the repulsive force of dark energy accelerates the overall expansion, it begins to oppose the very process of gravitational infall that builds cosmic structures. It acts as a kind of cosmic drag, making it increasingly difficult for those gravitational eddies to form and for galaxies to be pulled into the densest regions of the web. The river's current isn't just flowing faster, it's starting to dampen the ripples on its own surface. This creates a unique and measurable signature. In a universe dominated by dark energy, the peculiar motions of galaxies should be systematically quieter than we would expect in a matter-only cosmos. The violent streaming motions of galaxies toward immense superclusters, which would have been more pronounced in the past, should be slowing down. The universe isn't just expanding, it's beginning to smooth itself out, ironing out the wrinkles of its own large-scale structure. By meticulously measuring the peculiar velocities of millions of galaxies across different cosmic epochs, astronomers can trace the growing influence of this repulsive force. They are essentially taking the cosmic pulse of gravity itself, watching as its heartbeat grows weaker against the rising tide of dark energy. The next generation of redshift surveys, with their unprecedented volume and precision, will create detailed maps of these motions, allowing us to see not just where the mass is, but how it is moving in response to the dual forces of gravitational attraction and dark energy's repulsion. This isn't just about measuring speed, it's about taking the temperature of the cosmos, diagnosing the health of gravity in an accelerating universe, and uncovering a dynamic, living portrait of dark energy's relentless push against the pull of creation. Now we arrive at one of the most profound and philosophically challenging mysteries of all: the unsettling possibility that the value of dark energy is not a random accident of physics, but a prerequisite for our own existence. This is the anthropic principle, a concept that forces us to confront the deeply strange coincidence that the universe appears exquisitely fine-tuned for life. The numbers are almost too perfect to believe. If the strength of dark energy were just slightly stronger by a factor of only a few dozen, its repulsive force would have overwhelmed gravity in the universe's infancy. In that scenario, space would have expanded so ferociously that not a single star, planet, or galaxy could have ever formed. The cosmos would be a forever empty, featureless void, devoid of any structure or complexity. Conversely, if dark energy were significantly weaker or even slightly attractive, gravity would have dominated completely. The universe might have collapsed back in on itself in a devastating big crunch long before life had any chance to emerge. We find ourselves in a breathtakingly narrow window where the values allow for a cosmos that is both structured and long-lived, a cosmic Goldilocks zone where the forces are just right. This apparent fine-tuning seems to demand an explanation beyond mere luck. The anthropic principle offers a controversial but compelling answer. The universe is suitable for life because if it weren't, we wouldn't be here to observe it. In its weakest form, this is almost a tautology, a statement of obvious selection bias. We cannot observe a universe incapable of producing observers. But in its stronger forms, the principle points toward a truly mind-bending possibility, the existence of a multiverse. The idea is that our universe, with its specific set of physical constants and laws, might be just one bubble in a vast, perhaps infinite, foam of universes. In this grand cosmic landscape, each universe could have its own unique laws of physics. Some might have no dark energy, others might have so much they tear themselves apart instantly. The vast majority would be sterile, lifeless voids, but in a few rare universes, by pure statistical chance, the numbers line up perfectly to allow for galaxies, stars, planets, and ultimately life. We find ourselves in one of those habitable universes not because it was designed for us, but because we are a product of its specific, life-allowing conditions. This idea transforms the coincidence problem from a disturbing puzzle into a potential prediction. The value of dark energy we measure isn't a fundamental law waiting to be derived from a grand theory. it is an environmental outcome, a local byproduct of our particular cosmic address within the multiverse. While this view can feel like a philosophical retreat to some scientists, a way of explaining away a problem rather than solving it for others, it is the most natural conclusion. It suggests that the quest for a single, unique theory explaining why dark energy has its specific value may be misguided. There might not be a why beyond the stark reality that this is simply one of the few values that permits our existence. The multiverse concept, while still speculative, finds support in several cutting-edge areas of theoretical physics, most notably in the theory of eternal inflation. This model suggests that the rapid expansion of spacetime that occurred during the universe's initial inflationary period never truly stopped. Instead, it continues forever in a background state, occasionally relaxing in localized pockets to form bubble universes like our own, each with potentially different physical properties. String theory, a candidate for a theory of everything, also suggests a vast landscape of possible universes, perhaps 10 to the 500 of them, each with different configurations of extra dimensions and fundamental constants. In these frameworks, the multiverse is not just a philosophical fancy, but a natural consequence of our best physical models. Yet, the anthropic principle remains deeply controversial. Its primary criticism is that it seems to stifle scientific inquiry. If we simply accept that constants are what they are because otherwise we wouldn't be here, does that mean we stop looking for a deeper, more predictive physical theory? Many physicists vehemently resist this idea, arguing that true understanding comes from equations that dictate the constants, not from statistical arguments that allow them. Furthermore, the multiverse is, by its very nature, almost impossible to test directly. If other universes are permanently disconnected from our own spacetime, can we ever gather empirical evidence to confirm their existence? Some theorists propose that rare collisions between our bubble universe and another might leave an imprint on the cosmic microwave background, a circular pattern that would be the ultimate cosmic signature. So far, no such evidence has been found. The debate between the anthropic explanation and the quest for a fundamental theory represents a fundamental fork in the road for cosmology. It asks whether the deepest laws of nature are unique and inevitable, or whether they are more like a cosmic lottery ticket, one that we, against all odds, happen to win. This isn't just an academic debate, it shapes the entire direction of scientific research. Are we searching for the one equation that defines reality, or are we mapping the contours of a single habitable region within a far vaster and more bizarre cosmic ensemble? The value of dark energy sits at the heart of this question, a constant that is either a profound clue waiting to be deciphered or a quiet announcement that we are living in a very special place for now. And so we arrive at the final, and perhaps most humbling, mystery, one that transcends telescopes and equations to question the very nature of our quest. For centuries, humanity has looked to the cosmos seeking order, a grand design that would confirm our intuition that the universe is fundamentally comprehensible. We found breathtaking harmony in the laws of physics, a clockwork precision in the